Oops. Over the past few lectures, we have been trying to understand a typical instruction set architecture, which means the instructions, what their meaning is, how they are represented. So all these aspects of a processor as seen from a programmer's point of view. Now we'll go across the hardware software boundary and try to see how a processor is built, the microarchitecture part. So given an ISA, how to design a microarchitecture, that is the topic we are going to discuss over the next few lectures. So there are, of course, numerous ways of doing this, and different approaches, different solutions would provide you different combinations of uh, cost, power consumption, and other factors. So for a real system of substantial size, you need to use tools to do it. Okay, you need CAD. CAD stands for computer aided design. CAD tools to help in analyzing the trade-offs between these parameters. Okay, the number of possibilities may be large, and it may be difficult to manually figure out which is the best approach. And also, once you figured out the way of implementing, you need tools to take your design from that point onwards and get finally the physical implementation. So in fact, as we discuss in the lecture, you would also start on this exercise of building a small processor. So we'll take subset of ARM instructions and actually design the processor. So I'm assuming that you are familiar with VHDL, and also I'm aware that you haven't done much of practical work. So we will keep that in mind, but still I think it is essential to go through this exercise of trying to do design and get a real feel of it. Okay, so like any other digital system, you can view CPU or processor in terms of a data path and controller. So data path is where computations are done, data is manipulated, stored temporarily. Of course, there's a bulk storage in memory, which is a separate module. But within the CPU, some temporary storage is required. And controller is the one which orchestrates the whole thing. It sends signals at different times to do different things. And in return, it would look at some results of some operations being done in data path to decide its future course. Okay, so there are status signals going from data path to controller and control signal going from controller to data path. Now, looking at the instructions we have talked of, it's not difficult to visualize some major building blocks which we have to be concerned with. So there is an ALU, okay, which will do arithmetic and logical operations. You have a shifter which does shifting operation, multiplier which can do multiply or multiply accurate operations, register file which holds the local data, and interconnection path between processor and memory. So I'm calling this as PM path. So this is not just a question of connecting data from processor side to memory and memory to processor, but you have things like byte addressing and half word addressing and so on. So this has to take care of that as well. So just to repeat that. So ALU would take two operand and produce a result. So it's a block with two inputs and output. Shifter would take some data and perform shift as indicated by some control signals. Multiplier, register file. Register file, you would be accessing multiple operands from register file. So for example, ALU instruction like add R1, R2, R3 needs to pick up R2, R3 from register file. So I'm showing two outputs from this. When the operation is done, the result goes back to register file. So there is an input coming into the register file. These are what are called ports of the register file. And connection with the memory sitting on the other side, you have a block which actually sort of manipulates the data flowing from processor to memory or vice versa. Okay, so these are the key components or major blocks, and some additional circuitry is required which will glue these together, which will connect these. So that we will see gradually. But let's first focus on each individual part in isolation. Okay, we are going, next exercise would be to see how we can put these together to actually carry out the instructions. Okay, each one has a now very well defined role. So you can just while designing, let's say, shifter, you can forget about everything else and see how data can be shifted and so on. So later we are going to see how we fetch instruction from memory, how we decode it, how we make operand picked up from register file or memory, how we update the total state of the system. So state updation means updating in memory, register file, program counter, condition flag, and so on. So whatever state changes are required, they also need to be done. We are going to focus on a small subset of the overall instruction, and these are the instructions we have talked about in various points. So you have these add instructions with add with carry, add, reverse subtract with carry, subtract with carry, and subtract. I've just put them in alphabetical order. So these are 6 arithmetic instructions. There are 4 logical instructions and bit clear, exclusive OR, and OR. 4 compare and test instructions. Okay, 2 compare instructions, 2 test instructions, 2 move instructions, 2 multiply group instructions, load store, branch with link, and software interrupt. So these are the instructions we have looked at so far. The basic ARM subset has a few more instructions, so just give you a quick glance of that. So we'll worry about details of those later if and when necessary. So with processor, there could be a co-processor. For example, we haven't talked of how to work with fractional data, floating point numbers. So typically, that is created as a separate module, and it has its own instruction. So CDP is an instruction which actually instructs the coprocessor to do various things. So CDP it's a general instruction. So there could be floating point coprocessor, there could be SIMD processor, whatever. So there could be multiple coprocessor, and CDP with certain parameters could instruct those coprocessors. Then there are instructions which allow you to move data between CPU registers and the coprocessor registers. So MCR move from CPU register to coprocessor register. MRC move from coprocessor register to CPU register. So this group of 3 instruction is for that purpose. Okay, so a few more. LDC, load coprocessor register from memory. and store co-processor register to memory. Okay, so these are co-processor instructions. We will not go into details of these right now. Then there is an instruction BX, okay, which stands for branch and exchange, and that is used to switch between ARM and thumb modes. Okay, so you may be doing ARM instructions to begin with, and at some point the system reaches a point where it has to sort of save energy, so you could switch to the thumb mode, and then you start getting 16-bit instructions which are more economic in terms of energy. The next two instruction, I think many of you have become familiar as you have gone through the lab and seen their use. LDM stands for load multiple registers, STM stands for store multiple registers. And there is a instruction SWP, which stands for swap register with memory. It allows contents of register and memory to be exchanged. So it might look very trivial instruction, and you would wonder why this is allowed as a separate instruction. The idea is to do this atomically, and that is important when you're talking of multiple processor or multi-core kind of scenario. So atomicity means that either the whole thing is done, that is both way data transfer happens successfully, or nothing is done. So it cannot happen that you have moved data one way, but then something happens, control gets transferred to maybe another processor and so on. So from multiprocessing point of view, this instruction is important. So we'll leave these at this point and come back to the set of instructions we are trying to work with. We have DP instructions, as I just showed in the table a couple of minutes back: arithmetic, logic, test and move, branch, multiply, and data transfer. So first let's look at the issue of ALU design. Okay, for DP instruction, it is very easy to conceive that ALU has to do the required operation, add, subtract, and or comparison, or whatever is required. That's performed by the ALU. Okay, but ALU also could be playing a role in other instructions. For example, in branch instruction, there is an issue of calculating the target address. Okay, because the address in the branch instruction is provided as an offset from PC plus 8, so that addition is required, and that can be done by ALU itself. Okay, in multiply group of instruction, there is multiply and add. So typically multiplier is much more complex than adder, subtractor, comparator, and so on, and is built as a separate unit. But you can choose to put another adder with that multiplier for multiply accumulate instruction, or try to use the addition capability of ALU. Okay, so both kind of designs are possible. The trade-off would be between duplicating the adder and the circuitry required to share the adder, share the ALU for MLA instruction. Okay. Then for DT instructions, also again memory address calculation is required. So that is typically done by ALU itself. So here is the table of what ALU is supposed to do for different instructions. So in the first column, I have listed all the 16 DP instructions. Okay, there are arithmetic instruction, logical instruction, compare and test, and move instruction. All those are there. And in the instruction, there is a 4-bit field, as you would recall, which can which specifies one of these 16. Okay, so here is the code written for that. And on the right side, I'm showing what operation is actually done by ALU for these instructions. Okay. So some of these are obvious. I'll come to subtraction and all in a moment, but and, or, and exclusive or, add with carry. So add with carry, I'm showing as plus C, which means the carry is getting added. Test, for test, basically we need AND operation. For TEQ, we need exclusive OR operation. Okay. Uh, Logical OR operation. Move, simply OP2 is passed on. OP1 is first operand, OP2 is second operand. So now remember that ALU doesn't know whether the operand is coming straight from the register file or it's coming with some rotation. So that all that is happening outside it. Okay. As far as ALU is concerned, it looks at two operands, and what this 4-bit field indicates performs the operation. Okay. So ALU is a combinational circuit. Given these inputs, it instantly responds with the result. Okay. When I say instantly, that's a sort of idealization. In practice, there is certain delay, propagation delay. It's a combinational circuit. So whatever gates it consists of, there is gate delay associated. Okay. Uh, Moving on, this bit clear is OP1 and not of OP2. Okay. Move N is not of OP2. Okay. Now let's come to these subtract ones. So subtraction is being done by taking 2's complement of the second operand. So how do we do that? Essentially, not of OP2, which is complementing every bit, and 1 is added. Okay. Reverse subtraction, we complement the first operand rather than the second operand. Subtract with carry, C is added in addition. Okay. And compare also basically does the same thing as subtraction. And compare with negation, instead of performing subtraction, it does addition. Okay. So now looking at this whole sequence, whole list, you have basically addition, AND operation, exclusive OR operation, and complementation. So with these capabilities, you can cater for all these instructions. Is there any question at this stage?
So basically, so the ALU does not handle multiplication, right? That is a different unit.
Yeah, multiplication is a different block.
Okay.
So what are coprocessors?
Coprocessors are uh, uh, basically module which sort of augment the capability of a processor. Okay, so for example, floating point coprocessor. What it does is that all the floating point operations, that is fraction working with real numbers or fractions, uh, it takes care of. Okay, so the capability of a processor can be extended by adding coprocessor, which can do some specialized functions.
All right, sir. So the multiplier, the block that does the multiplication, is it also called a coprocessor?
Uh, well, if you're including, you can see technically whatever is there in coprocessor could be directly involved in directly included in the processor. Okay, it's a matter of how you want to partition. You can, for example, in this version of ARM, there is no divide instruction. All right. If you have to add divide instruction, it has to be beyond that. From let's say commercial point of view, or from a product point of view, you can have product with different options. So you may, if your requirement does not need a particular coprocessor, you can get a system without that coprocessor. So there are some systems where the coprocessor will be essential, essential part of it. It's just that from design point of view, they have been modularized. Okay. Also, there are situations where these become optional items. So you may buy a configuration with coprocessor or without coprocessor. So what I'm saying is that this division between processor and coprocessor could be from design point of view, or also from point of view of defining different product configurations.
Yes, sir. Understood. And so one more doubt. In the thumb mode, are there a different set of 16-bit instructions?
These essentially same instructions with some restrictions. For example, instead of doing add R1, R2, R3, you may be doing add R1, add R1, R2, which means that R1 is acting both as one of the operands and destination. Okay, because you are reducing the size to 16 bits, instructions get somewhat restricted.
Got it, sir. Thank you.
Okay, so continuing with what ALU is supposed to do, here I'm looking at what ALU does for non-DP instructions. Okay, for load store, it can perform addition or subtraction of the offset. Okay, and whether it is addition or subtraction is dictated by a bit which we labeled as U. So in the opcode field, it had 6-bit opcode field. One of the bit was labeled as U, which stands for whether offset is offset is upwards or downwards, or to be added or subtracted. So both options are shown here, and you can have load with offset added or offset subtracted, and similarly store. For branch and link, the offset is added, but offset itself is a signed number. Okay, so this itself could be positive or negative. And plus K I'm showing because, as I mentioned, typically it is PC plus the offset plus 8. Okay. Now that 8 could also be implementation dependents. So I'm just putting a K which could be 0, 4, 8 or whatever. All right. Then for multiplication, ALU, I mean this multiply operation may be done outside, but for MLA the addition can be included as part of this ALU operation. So the product itself will be one operand, and this OP3 would be the second operand coming in. Okay, now apart from designing an ALU, one has to keep in mind that these many of these instructions have some variations and suffixes. So suffixes in terms of predication. So you could say add equal ADD EQ, which means you need to perform addition only after testing the condition, and whether instruction sets a flag or not. Okay. Then there are options like you are for load store instruction, whether you are moving one word or half word or byte. Okay. The operand itself has variation in terms of shifting and rotation. The address could be pre-increment or decrement or post-increment or decrement. Okay. Auto increment decrement, by auto I mean that the address register is updated. Okay. So you may have auto increment or decrement, or you may not have. So we need to be concerned about these variation suffixes also. So for the group of instruction we're talking of, I'm showing what suffixes are possible for which instruction. So condition can be put with any of these. Okay, you could have arithmetic operations done conditionally, logical, test, move, branch, multiply, load, store. All instruction have a condition field. Okay, so condition could be suffixed with any instruction, and S, which indicates whether the flags have to be set or not, that also is put as a suffix. So this is as seen from the assembly point of view. And at machine code level, there is a S field, 1-bit field, where you can put a 1 or 0. So not all instruction can have S suffix. Branch instruction cannot have. And load store cannot have. Okay. For testing, it is assumed you don't have to say, you don't have to put S. It is assumed that the flags will always be affected. Okay. Here with load store instruction, I'm putting an additional thing as BH, SB, SH. So B is for byte, LDR B, for example. LDR H would mean load half word. Similarly, SB is for signed byte and signed half word. So this shows in terms of instruction representation where these things are put. Okay. So in DP instruction, this is the S field, right? The condition field is here, leftmost in all instructions. And within the operand 2 field, you have rotation and shift provisions. So we have discussed this, so I'll not go into that further. And in DT instruction, you have that up-down bit as part of OPC, and operand 2 has provision for providing shift. Okay, either you have a constant or you have shift. You have register with possible shift. Okay, so now let's start looking at these building blocks from design point of view. So we think of ALU as something which has two 32-bit inputs, bringing in the operands. It can take input from carry flag, so there is carry in, and there is something which tells it what operation it has to do, and it produces a 32-bit result. Apart from that, it outputs certain conditions, okay, some information which can be used to set conditional flags if the instruction demands that. Right, so this output will go to destination of the result as specified the instruction. Operand will come from the operand fields. They'll come from either register file or constants as specified by various fields of the operand. So let's look at a simple example of add circuit. Right, you are I'm sure aware that you can have different adder design. You could have carry propagation or carry lookahead depending upon the cost performance trade-off you want. So in most simple case, you have a full adder or 1-bit adder with the two 1-bit operands, carry in, carry out, and a sum. And you can cascade 32 of these to form a 32-bit adder. Okay, so that is, I think, something well understood. And subtraction utilizes same adder by taking 2's complement of the second operand. So what we do is we can complement bi, and for this one addition, we can make the initial carry input as 1, and rest of the carry propagation takes place as it is. Okay, so this is subtraction circuit, same as adder circuit with these inverters and carry as 1. We can combine, we can sort of have same adder by making a provision for feeding the same input either directly or through inverter. Okay, so I put a multiplexer here. You can also have, and you can use XOR also, but just for conceptual clarity, what I'm saying is that there is a control signal called B invert, which allows either BI to go directly to the adder or through the inverter. Okay. So now instead of adder, if we take this box and replicate it 32 times, we can get a 32-bit unit for performing addition and subtraction. So this initial carry needs to be controlled, and it is same. Yeah, the power has failed, so you may see my picture darker, but I'm sure you can keep looking at the slides. So B inverter is playing two roles. It tells you whether the initial carry is 1 or 0, and secondly, whether the second operand has to go with inversion or without inversion. The circuits for AND or XOR instructions are straightforward. You want to perform bit by bit AND, bit by bit OR, bit by bit XOR. Okay, so arrays of 32 AND gates, array of 32 OR gates, and array of 32 XOR gates is what you need. So we combine that into same box and put a 4-to-1 multiplexer here at the output. Right? So you have AND or XOR or adder feeding to these 4 multiplexer. So depending upon how you select this multiplexer, you can have at the output bit by bit AND of input, or 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 XOR or addition or subtraction. Okay, so now think of the ALU as an array of 32 such blocks. Okay, and the control inputs are one is this input control, or okay, I'm sorry, I missed this. So instruction like move simply want operand 2 to be passed on to the destination. Okay, so we have put a multiplexer at the second input of the adder. So it can pass either AI or 0. So if 0 is passed, then BI will be made available at the output. So these two bits, 1 bit controlling this mux, 1 bit controlling this mux, I'm calling as input control, and there is some control input controlling this multiplexer, which is in a way defining the operation to be done. So you can imagine that this 4-input multiplexer would require 2 bits to decide its function. Okay, so you need control of all these multiplexer, and this ALU can perform all the functions we need. Yeah, just excuse me for a moment. हेलो, हाँ मैं आपको 12-1 के बीच में मिलूंगा, क्लास के बाद मैं आऊंगा उधर। हाँ ठीक है, ओके। Okay. So I have now made a provision here for complementing A also. Okay, as I hinted earlier that instead of a multiplexer, let me go back to this. Instead of putting a multiplexer here, you can simply XOR BI with this control input. Okay, so if this control input is 0, BI passes as it is. If it is 1, BI gets complemented. Right? And instead of this multiplexer, I can have AND operation. So if this input control is 1, AI passes. If it is 0, 0 passes. Okay, AI gets blocked. So simplifying these multiplexers, I have a provision of complementing AI or complementing BI. So this is required for reverse subtraction. Okay. And this can block AI so that you are able to pass on the second operand. Okay, any question at this stage? So this is the final picture of this 32-bit ALU. We have some inputs which are controlling, some control inputs which are controlling how A and B are passed with complementation, without complementation, or whether A gets blocked or not. And then you have 2 bits controlling the output side multiplexer. How this ALU is going to be controlled? The fields which are going to control are these fields. Okay, bit 25 to 27, 21 to 24, 4 to 7. So from these inputs, okay, so this one okay, let's skip that at the moment. So I would need to relate these to various fields. All right. So looking at different fields of instruction, we need to figure out what is the initial carry, what is the 2-bit multiplexer control, and what are the 3 signals for input control. So we'll tackle this later. So let's come to the compare operation. So there's compare instruction, CMP, and then CMN. What we are doing is that we are doing subtraction and looking at the result. Okay, so that's the approach we have followed. So as far as ALU is concerned, we instruct ALU to perform subtraction operation, and by looking at the result, we can see whether it is positive, negative, or 0. Okay, or even things like overflow. We can judge what has happened. Okay, what was the result of comparison. Technically, it is possible to do a direct comparison also. So you can build a separate circuit which does compare and nothing else. All right, and it can produce one of these results. Okay, now if the instruction requires, if instruction has S field and it requires flags to be set, how do we infer what value has to be put to what flag? Okay, so there is Z flag, which is to be made 1 if the result of computation is 0. So I'm indicating S0 to S31 as the 32-bit output of the ALU, which is constituting the result. Okay, so these 32 result bits, we OR all of these, okay, and invert. So if any of this is non-zero, you will get a 1 here and a 0 here. Okay, only if all of them are 0, you get a 0 and a 1 here, and you can set the Z flag to 1. N bit, which is basically indicating whether the result is negative or not. This can come directly from S31, the sign bit, leftmost bit. Overflow requires looking at the last two carries, C31 and C32. C32 is the final carry, which can be used to decide C directly. And for V, we need to perform an XOR of these two. Okay, so that's an additional circuitry which is required to enable us set the flags correctly. Okay, next question is how do we take care of predication? Predication means that you need to check a particular condition by looking at the flags. Okay, so recall that I had put a table. There is a condition field which can have values 0, 0, 0, 0 to 1, 1, 1, 0. So the last one is not used. The 15 combinations from 0 to 14, these are there. And their symbolic names are shown here: equal, not equal, carry set, higher or same, minus, plus, and so on. All these are there, less, greater than, equal to, and so on. And their meaning in terms of what flag values are we looking at is shown here in the third column. Okay, so EQ basically checks whether Z is set or not. NE checks whether Z is clear or not, and so on. So we need a piece of logic which will look at these 4 bits of the instruction, the leftmost 4 bits of the instruction, and look at the flags and decide whether the condition is met or not. Okay, so conceptually you look at this block as getting these 4 inputs. These are coming from 4 flags or flip-flops, 4 bits from the instruction, and it decides P, or the predicate, whether it is true or false. Okay, this we can use to enable execution of the instruction. Okay, so how do you disable add operation? What you could do is you could let add I mean, this need not do anything to the ALU. ALU doesn't look at this. ALU performs what it has to do, and this could be used to decide whether the result gets stored or not stored. Okay, this is how typically it is done. So P is used as an enable signal for carrying out state change. Okay, so now imagine that you have instruction like add EQS. So you are firstly predicating add instruction, and the instruction is also supposed to change the flag if it gets executed. So we if condition is false, if P is false, then we don't put the addition result in the destination register, and we also don't set the flags. Although it is add EQS, no state change will happen if the predicate fails. So here is a simple design to generate p-value. So this block which I showed, all right, what is the logic inside this is here. These 4 bits of the instruction, the condition field, is used to perform selection through this multiplexer. Okay, so it selects which of, now this is the logic which is taking care of each individual condition. So if this field is 0, we simply pass on Z value. If it is 1, we pass on bar of Z, complement of Z. Then C or complement of C, N or complement of N, V or complement of V. Then we had, for example, let's look at some cases. So this one, which is, if you interpret this binary number, it is 8 C set and Z clear. So it is AND of 2 things, C and the second one is coming from Z bar. Okay, so this is outputting C and Z bar, and if the condition field is 8, this gets selected. Okay, its complement is 9. Let's look at this one, N equal to V or N not equal to V. This is binary 10 and 11. So 10 basically is exclusive OR of N and V. Okay, and 11 is complement of that, and so on. So you could relate this to the table which we had shown earlier. So having done this, we have an ALU which can do these instructions: add, subtract, and XOR, or bit clear, both, compare and test, move. Okay. Actually, we took care of reverse subtraction also and add with carry. For reverse subtraction, we can either include multiplexer to switch between OP1 and OP2, or include option to invert OP2. So the design which I've shown, we had gone for this. We included an option to invert OP1. Okay. The other way would have been to interchange operand 1 and operand 2. And the way we have taken care of this add C, subtract C, RSC, the initial carry can be a constant 0 or a constant 1 or the C flag. These are 3 options which can be fed to the initial carry input. Okay. Next we look at how do we get operand 2. So there are variants in operand 2 because they could be a choice between register and a constant, and secondly they could be shift and rotate options. Okay, so shift can be, amount of shift can be decided by a register or it could be a constant. So let's try to design a circuit which can perform these shift operations. Okay, again this will be a combinational circuit. All right, we get an input and it responds with a shifted output. Where it gets stored, where it comes from, that all that is outside it. It's simply a combinational circuit uh, which will manipulate the bits of the input by in a suitable manner. So you have to input shift amount and shift type. Also remember that shifting can generate its own carry, and while setting the carry flag, you would need to select the right candidate for carry. So they were just recalling what shift types were. This is shift left logical by 3 position, shift right logical by 3 positions, shift right arithmetic by 2 position is shown here. So you can see that A31 is repeated. Okay, the 2 gaps have been filled by sign bit. So a circuit for shifting by 2 bits is shown here. Just for simplicity, I'm showing only 8-bit data. Okay, 8-bit data. If we have to shift by 2 positions, you have to insert 2 zeros. Okay, so you're selecting one of these 2 bit vectors. First bit vector is same as the input, and second one you can see that you have shifted these signals. These 2 are thrown out, and 2 zeros are included. So the multiplexer selects one of these. This is a sort of conditional shifter. You can either it selects between 0 shift and 2-bit shift. If you have to take care of carry, then this the last bit which is getting thrown off is to be used to set carry flag. Okay, so I'm showing a selector which allows either this carry to go through or this carry to go through. Okay, so this carry is coming from ALU. So there are 2 sources of carry. One is a shifter, other is the ALU, and depending upon what the instruction is, one of these carries is used to set the carry. This circuit shows a combined circuit which can perform these rotation right, arithmetic shift right, and logical shift right. So all 3 are right shifts with small difference. Okay, these 6 bits these 6 bits are same in all cases. Okay, whereas 2 of the bits, these 2 bits are coming from a multiplexer. This multiplexer takes care of which shift we are talking of, and it's guided by an input called shift type. Okay, so in case of rotation, the first option is rotate. So the bits which are getting thrown off are fed on the other side. Okay, the second case is that of arithmetic shift right. So the sign bit is actually replicated in these 2 positions. And third is logical shift where 0 is sent. So how you decide these bits which are going in the vacating positions, either coming from the other side or sign bit or 0, decide which kind of shift it is. Okay, and in all cases the carry bit is coming from this position. So is this clear, this circuit, or any questions?
Sir, what is the carry in over here?
Carry in is the carry. Sorry, maybe this terminology is confusing. For this circuit, it is carry in and there is carry out. Basically, what I meant was that this is a carry coming from ALU.
So basically, the multiplexer has to choose between which one to set.
Yeah, multiplex has to choose. So uh, if in arithmetic instructions, uh, if there is no operand shift, then it is this carry which prevails. If there is shift, then the carry coming from shifter will prevail. So uh, one could have some logic to decide which carry has to be selected, and that carry is passed on to the carry flag.
Okay, sir.
Yeah. So with respect to this diagram, what I have done is that instead of just feeding two zeros here, I have made these three options corresponding to different types. Okay, so feeding zero is still there as third option for LSR. For ASR, it is sign bit which is replicated, and for ROR, it is the two LSBs which would have been lost. They are selected. So this multiplexer is a three input, one output multiplexer. Each input or output is 2 bits. This multiplexer is 2 input, 1 output multiplexer, where each input and output is 8 bits. I'm showing a simplified case for 8 bits. Same thing you can extend for 32 bits. And this is a plain 2 to 1 multiplexer. Everything is 1 bit. Okay, now how do you build a general multiplexer which can perform any shift from 0-bit positions to 31-bit positions? So here I have illustrated this with a fixed shift amount, which is 2. So individually you can design circuit which can shift by 2 positions, 3 positions, and so on. But here we are trying to look at a circuit which can shift by any amount going from 0 to 31. So 0 means that you don't need any shift. Okay, so the input has to be passed as it is. This is built using 5 stages. Okay, where is 5 coming from? 5 is the log of 32 to the base 2. And each of these is a fixed shift amount multiplexer, is a shifter with fixed amount. First one can shift by 1 position, this by 2 positions, 4 position, 8 position, and 16 positions. So uh, each one can either do no shift or shift by a fixed amount as shown here. So by suitably controlling these, you can get any amount of shift, because suppose you want to shift by 10 bits. Okay, so which means you look at 10 as a combination of 2 and 8. So you allow this to perform 2-bit shift, allow this to perform 8-bit shift, and instruct others to perform no shift. So you will eventually get a 10-bit shift here. All right, so any 5-bit number can be used as shift amount, and that number simply needs to be fed to these select inputs. Okay, now I talked about circuit for doing 3 different kinds of right shift. Okay, but there is a left shift also. You can, so there are various ways of doing it. On similar principle, you can design a left shift circuit. Okay, and you can maybe cascade these two. So each of these is capable of doing 0 shift. All right. So if you want to perform left shift, you control this appropriately and ask this one to do no shift at all, and vice versa. Okay. So you basically one of them will actively do some shift, other will do nothing. You can also put them in parallel like this and then have a selector. Okay. So what is the difference? Uh, the first option is going to have more delay as compared to the second one, as you can see. All right. So whether it does nothing, there is some delay it encounters through the multiplexer. Okay. This one has more wiring and one extra multiplexer, but it has slightly lower delay. Another most economic way of doing is that we already have a right shifter. Okay, so you bit reverse the input, perform right shift, and then bit reverse again. So you'll get effectively a left shift. All right. Now bit reversal, it could be done simply. It's a matter of simply wiring, just changing the wire positions, and a multiplexer will select whether it allows straight input or reverse input. And similarly here. So this is the least expensive circuit. Compared to this one, this will have still more delay because you have a multiplexer stage here, multiplexer stage here. This one encounters only one multiplexer stage. So you can see that there are a couple of simple options with different performance and cost trade-offs. Okay, now we said that we want to use ALU for address computation in load store instructions. So as far as ALU is concerned, we have provided for addition and subtraction. Therefore, it can add the offset, subtract the offset, both it can do. And the question of pre or post increment or decrement is something which can be handled outside. It's a more a question of sequencing things. As far as ALU is concerned, it has to perform addition or subtraction only. Whether it is done before memory access or after memory access is a matter of ordering the operation or timing the address computation and memory access. Okay, so as far as ALU is concerned, nothing needs to be done. And the question of auto increment decrement or not is also a question of whether the updated address is put back in the base or not. Okay, so for ALU again, nothing additional is required. We need to make arrangement for doing partial word transfer. Okay, whether we have instruction which deal with a byte, half word, or word. Okay, we are talking of load store. So selection of a byte from a word could be done by a multiplexer like this. Okay. So I'm showing word 32 bits are broken into 4 groups of 8 bits or bytes. Okay, so multiplexer needs to select one of these. And where this selection input will come from, it will come from the least significant 2 bits of the address. Okay. Now, seeing from other side, when your data is coming as a byte and you want to make it a full word. So there are two ways of extending it. One is extending with zeros, other is extending the sign bit. That is reflected here. So you have 8 bits and remaining 24 bits can be filled with zeros. That is zero extension. Or they can be filled with the leftmost of these 8 bits. That is a sign extension. That is straightforward. So now this from memory you would be getting, let's say you are doing LDRB or LDRSB, right? From memory you will be getting a full word, and only one byte is going to come out of this multiplexer. But in the processor you need to uh, fill up the entire register, and there the sign extension or zero extension will come into picture. Similarly, if it is LDRH or LDRHS, LDRSH, you will select one of the two halves and then do extension and send to the processor. This is shown. On the other hand, what happens when you have word coming from processor, but you need to write only a byte or half word into the memory? So store byte. In memory, you don't do any extension. Okay. If the instruction is store byte, only one byte in the memory is affected. It is not that zeros or sign bit get filled in rest of the word. So so now imagine that memory is organized as physically word memory. That means in memory physically you can write an entire word or read an entire word, but we are getting only a byte from the processor to be written into 1 byte of memory. How do we do that? So effectively you need to let's just, for an example, let us say it is this byte. I mean, from least significant side, it is a second byte which is to be written in the memory. So what we need to do is we need to read the memory word, entire word, which is 4 bytes, and 1 byte needs to be substituted from the byte coming from processor, and the whole word is written again. Okay. So that is if memory works purely in terms of word. Okay, you need to you are allowed to modify. You are allowed to write only entire word. Then you need to maintain 3 bytes as it is. Therefore, what you do is you read 4 bytes from memory, replace 1 byte coming from processor, and then write it back. The picture I'm showing here is if you have separate write enables for each byte. Okay, then you can perform this operation easily. You enable only 1 byte to be written, and that data which is coming from the processor, 1 byte coming from processor, is written to the required. It goes to all of them, but it gets written in only one of the 4 places. So these two scenarios may exist depending upon how memory is organized. Okay? Whether it has write enable for entire word, a single write enable, then you need to have read followed by write. If it has write enable for each byte part, then you can do it in single shot, just modify 1 byte. And same thing is in the case of a half word. Okay, in this case, you will enable this part to write or that part to write, depending upon the address. Okay, finally coming to another module of the processor is register file.
Excuse me, sir.
Yeah.
Sir, when you said that we do LDRB or LDRH, you said that we load only 1 byte from the memory and then fill the rest with the sign extension, right?
No. LDRB or LDRH means that we are loading from memory to register.
Yes, sir.
Okay. So we get 1 byte from memory. Either we'll get whole word and then pick up 1 byte, or we'll just get 1 byte itself. And the entire register needs to be modified. Okay, the entire register will get filled with that byte with one of the 2 extensions.
Oh,
So
all right.
semantics of load byte or store byte is slightly different. In load byte, the entire register is updated. In store byte, only 1 byte of memory is updated. No extension.
Sir, so in that case, let's say that sign extension takes place.
Yeah.
So in that case, then how would the register differentiate with whether it's a full word coming or a single byte with sign extension?
Uh, so you see, ultimately, this block which I labeled as PM processor memory path, in that we are actually taking care of any extension which is required. Okay, selection of byte, extension, all that is part of that one. So as far as register file is concerned, entire register will get read or written. Okay, so we are assembling, we are putting together 32 bits to be written into register. So let me get back to this extension one. Okay, so extension of a byte into a full word is shown here. So as far as register file is concerned, 32 bits will go there for getting written. Okay, I don't have a complete diagram, but so it's like this. So we need to put these pieces together. I'm showing them separately. So when in a LDRB instruction, we pick up a word from memory and select a byte out of that. Okay, so suppose address was 1002. So 1002 byte address would mean it is word number 250 and within that byte number 2. You getting it? So word number 250 is read and byte number 2. So these bytes correspond to 1000, 1001, 1002, 1003. Word number 250 consists of these 4 bytes. So we would select this byte number 2 And now before we send it to register file, so when I say byte to processor, it means this is going to the register file. It will get extended by sign or extended by 0, depending upon whether it was LD, LDRB or LDRSB.
Yes, sir. So my question was, if it is extended in such manner that is the rest of the 3 bytes are also filled up with the most significant bit.
Yeah.
So what I was asking is, how would the like there could be an identical word also, right? Which has the same 3 bytes filled with MSB and the last byte. So how would the register differentiate whether we loaded a byte or we loaded a word?
Uh, so as far as register file is concerned, it doesn't distinguish. It just takes in 32 bits and writes. Okay, whether it is coming as a result of LDRB or just LDR, it doesn't know, and it need not know. So whatever has to be written into register file is prepared by this part of the circuitry.
Okay, sir.
So here there's a conceptual picture of register file. Since we have 16 registers, each of 32 bits, it has data in and data out, okay, which are 32 bits. And there is a 4-bit address. Then there is a signal which tells you whether to write. So you could arrange it so that reading is always happening. Whichever address is there, output of that particular register is available here. But writing involves state change. So an active signal here would cause this data to be written in the register specified by this address. Okay. But we actually need a register file with 2 ports. So I'll come to that in a moment. You could visualize this as basically 16 registers, R0 to R15. Their outputs could be multiplexed based on the register address, and you have that data out. And the data in can be demultiplexed to all of these. So although I'm showing demultiplexer, but conceptually this data could be just going into this, and depending upon address, one of these would be clocked. Okay, so you could clock one of the 16 register as selected by this register address. And data could actually be not really demultiplexed, but straight away going to all these 16 registers. This is more like the register file we need, because we need to fetch 2 operands. So there are 2 data outs, read data 1, read data 2, with different addresses. So you don't have a single address, you have 2 read addresses coming in, 1 write address coming. Each of these is 4 bits, and you have write data. So this, you can consider this as register file with 2 read ports and 1 write port. Okay, so 2 R plus 1 W ports, 2 read ports and 1 write port. But what is our requirement for our register file ports? So if you consider an instruction like this, add R1, R2, R3, LSL, R4. So shift is being specified by a register. So this requires to read 3 registers, R3, R4, R2, R3, R4, and 1 write to R1. So these are some extreme cases. Instruction like LDR R1, R2, R3 with exclamation, it means that the computed address is also written back to R2. So similarly, even if it is post increment, so this is pre increment with register write, with update and post increment with update. So this requires each of these requires two reads. You need to read R2, R3, and it also requires two writes. You need to load the data coming from memory into R1, but you need to update R2. So two writes are required. What about store with auto increment? It requires three reads and one write. Okay. You need to read R1, R2, R3, and the address updated in R2. So apart from that, each instruction requires reading PC, which is nothing but R15, and also writing into PC, because each instruction will update PC. So how do we deal with this? So there are two choices. Either you provide additional ports in the register file so that all this can happen very efficiently, or you try to sequentialize some operation. So if you are implementing instruction in such a way that it is allowed to execute in multiple cycles, then you don't need to do all of these in a single cycle. Okay, you can with limited ports, you can sequence your operations and work with register file with smaller number of ports. So actually, logically, you can provide any number of ports with the register file. You need additional circuitry for multiplexing, demultiplexing, etc. But it becomes more and more expensive. You know, the adding ports to a register file means increase in the area, chip area, increase in delay, increase in power consumption, and therefore, very common approach is to just leave register file with two read ports and one write ports, and try to take care of the rest by spreading over time or even space. So for example, I'll show you a scenario where PC can be a separate register. So here, although logically PC is part of this register file, okay, it can be made a separate register. So here I'm showing PC as a separate register, and output of this goes to get an instruction from the memory. And this PC is incremented by 4, so PC plus 4 is sent back to this. Now, the issue is that PC is simply R15, so it can be appearing. It is not just for instruction fetch. Instruction which instruction like R15, add R15 comma R15 comma 10, for example, would mean that we want to add 10 to PC. So we'll have data coming from ALU or memory, which is normally going to a register, but it is also could be used to write into PC. So we need this path. Okay, data coming from ALU or memory gets written into PC, which is here. Okay, so PC can be written by normal PC plus 4, or as the result of some other instruction, it can be updated. So actually here, the what we are doing is we are maintaining it in both the places. So there is R15 here, and its copy actually is lying outside, and when we are updating both. Okay, we can update this as well as that, and PC+4 also gets written into this. Okay, so that is all for today. Sorry, where is, yeah. Any questions before we close? Okay, thank you.